So because we didn't have class yesterday and I was not able to upload this video, I thought I would do a quick example of working through a hypothesis test for proportions so that we could see how to do that with JUMP rather than with the tables, because we won't be using the tables in this class. So this is the example that's in the notes, and you can find the data and other data at this website. It's from the AmStat News. So the question is dealing with technical writing on the job for graduates from undergraduate statistics programs. So the American Statistical Association conducted its first ever survey of graduates with a bachelor's in statistics starting with the class of 2016. The results for that survey are summarized and discussed in AmStat News. Looking at table 6 on page 11, which is this table here. And so the question is it plausible at the 0.05 level that fewer than 75% of 2016 graduates from undergraduate stats programs are rarely or never doing any technical writing? So I'm going to ask you to pause this and with a partner or on your own answer the usual 6 questions. So identify the population, identify the variable being measured, identify the type of variable, what is the answer what the parameter of interest is, what is the sample statistic, and what is the sample size. So the population that is of interest is 2016 graduates of undergrad stat programs. The variable is whether they rarely or never use technical writing on the job. Because this is a yes-no kind of question, this is going to be a qualitative variable. The parameter of interest is the proportion or the probability, but we'll call this the proportion, in the population or the true proportion of 2016 undergrad graduates of stat programs who rarely or never use technical writing on the job. The sample statistic is p hat. So this is our sample proportion, and in our sample we had 44 respondents say they rarely or never use technical writing skills on the job out of a total of 128. So our sample proportion is 44 out of 128. And the sample size, this is n equals 128. So our hypotheses, we're trying to figure out if it's plausible at the 0.05 level that fewer than 75%, this fewer is a strictly less than question. So because there's no equality implied in that, that must be our alternative hypothesis. So our alternative and our null hypotheses comes from carefully reading the context and the statement of the question. So the null hypothesis must always have equality. And the alternative hypothesis must have inequality. And so with that simple rule, because there's an inequality implied in the question, the alternative hypothesis must be that inequality. So the hypothesis for the alternative must be that p is less than 0.75, and the null must be that p is equal to, or we can also write it as greater than or equal to 0.75. Those are functionally equivalent. And we define the parameter as p is the true proportion of undergrad graduates or graduates from undergraduate programs from stats programs in 2016 who rarely or never use technical writing on the job. Now that we know our hypotheses, we know what kind of test we would want to use to do that, and that would be a one sample z-test for proportions. We have one sample because there is exactly one sample of students or graduates that we have taken from the population, and there is one proportion that we are interested in. To check our conditions and assumptions, we need to make sure that we have a random sample, which we have. We need to make sure that we have a qualitative response, because otherwise testing a proportion makes no sense. So we have a qualitative response variable. We're good there. And we need to make sure that when we sample a sample of this size, we have at least 15 successes expected. So this is going to be n times p naught and n times 1 minus p naught are both at least 15. So we need to check, is n times 0.75 and n times 0.25 both greater than or equal to 15. And it turns out that is, so n here is 128 in each case. And we have at least 15 people expected to use technical writing more than rarely or never, and at least 15 people expected to rarely or never use technical writing, so we are good. So for the mechanics, the first step is to state your significance level. And alpha here was provided at 0.05. We're told to test this at the 0.05 level. So that's our alpha. And the second step of mechanics is always the same. It's always state your rejection rule, and we will always, always, always reject the null hypothesis if the p-value is very small. So if the p-value is so small that it is less than alpha, which in this case is 0.05, we reject the null. Now C and D is where it changes. C is find your test statistic, and this in this case, because we're doing a z-test, we have a z-obs, and I'm calling this obs because this is based on observed data. It is a statistic, so it's based on our observations, and it is our y bar minus, not y bar, getting ahead of myself. It is our p hat minus p naught over the square root of p naught, 1 minus p naught over n. This is in fact a z-score. It tells us how different our sample statistic is from the true proportion, if that really is the true proportion, if the null hypothesis is in fact true. It is a measure of unusualness. So our sample statistic was 44 over 128. Our hypothesized value was 0.75. And our standard error, if the null is true, the true standard error for the sampling distribution is 0.75 times 1 minus 0.75 all over 128. And we take the square root of that. And when I do my calculations, I get a test statistic of negative 10.614. And this is big. This tells me that I have a sample proportion that is 10 standard deviations less than the hypothesized value. So if the null is true, I've observed something that's 10 standard deviations away from it. That is very unusual. Right? So if you think about the empirical rule, all right, if we think about that 68, 95, 99.7 rule, if the true proportion were 0.75, 68% of the p-hats should be within 1 standard deviation. 75% or 95% should be within 2 standard deviations. And 99.7% of the p-hats that we obtain should be within 3 standard deviations of that 0.75. And what we did was we got something that was 10.6 standard deviations away. That's really, really unusual. Nearly all of our p-hats should be within 3 standard deviations, and we got something that was 3 times that. So something super far away. So how unusual is that? That's where we get our p-value. And this is what you've all been waiting for. We do this in JUMP. So the p-value is going to have to be something that's matching up with this idea of unusualness. Now, how do we determine usual? We go back to our alternative hypothesis. So because we're pointing to the left, because we have a less than alternative, we're going to look in the left tail of this distribution. So I come to my JUMP distribution, and this is a normal distribution with mean 0 and standard deviation 1. So the 0 and 1, that gives me the z distribution. And we remember that I'm going to input values and calculate the probability because the p-value, that p stands for probability. So I'm looking for a probability value. So I'm not going to change this. I want to get the probability associated with my z-score, my z-value. And we can see here that I have a left-looking value, a left-looking probability, because I want my left tail. So this matches what I want to do. If I were doing a right-tailed test, I would want this pointing to the right. And if I were doing a two-tailed test, then I would look in both tails, like this last option. Note that when I am doing a hypothesis test, I would never choose this third option. I only want left tail, right tail, or two tails. So I want this left tail. And we can already see that this kind of matches up with what I drew up here in the notes. So I've got 1 standard deviation away, 2 standard deviations away, 3 standard deviations away, and that's nearly the entire curve. That's 99.7% of the normal curve. And I want to go to 10, and 10 is going to be way down here, way off this screen. So I should expect a very small probability to the left of 10, to the left of negative 10. So I input my value, and I get a probability, this p-value, of less than 0.0001, because all the way down here at negative 10, there is very little probability that remains to the left of it, and that is my p-value. So my p-value, because I have a less than alternative, it's the probability that I get a p-hat less than negative 10. Or excuse me, not a p-hat, a z less than negative 10.614, or a p-hat less than 44 over 128. And that probability is less than 0.0001. Very small. So because I got a big z-score, I'm going to get a very small p-value. So we reject the null hypothesis. This p-value, that satisfies my rejection rule because the p-value is less than alpha, 0.05. It is plausible that fewer than 75% of 2016 graduates from UGrad STAT programs rarely or never use technical writing skills on the job. And that's why I'm making you do all this writing, because it was high probability you're going to be using these technical writing skills on the job. So once again, to find the p-value, you go to the distribution, the normal distribution. For example, if you're doing a z-test, You leave the mean and standard deviation alone because the z-distribution has a mean of 0 and standard deviation of 1. You want to input the value to calculate the probability, and you select the correct direction. So you want the inequality to match what you have in your alternative hypothesis, and you enter the value. And that's it.